In this highlight video, we will talk about thermodynamics versus kinetics. Even though this is a review from Gen Chem, it is important that we can distinguish between the reaction characteristics that are governed by thermodynamics and kinetics. There are two types of reaction energies. The first one, thermodynamics, remember, compares the energies of the reactants versus the products. And it's this energy difference that controls the equilibrium concentrations of the reactants and products during the reaction. Kinetics, in contrast, compares the energies of the reactants versus the energies of activation. And so it's the height of this activation barrier that controls the rates or the speeds of the different reactions. A practical component of thermodynamics is the equilibrium constant. Remember that the equilibrium constant is a constant for a reaction at a given temperature or pressure if the reaction was run in the gas phase. The equilibrium constant, remember, equals the concentrations of the products over the concentrations of the reactants. If there were coefficients in front of those reactants or products, remember that the concentrations would be raised to the power of those coefficients. When we look at this equilibrium constant, it tells us something about the reaction. If the equilibrium constant is greater than 1, that means that the numerator is bigger than the denominator, and because the numerator is the products, this would favor the products. Alternatively, if the equilibrium constant is less than 1, that means that the denominator is bigger than the numerator, and so this reaction would favor the reactants. Remember that we could start with any concentrations of A, B, and C, and that reaction will proceed to a point where the equilibrium constant is met by various concentrations of A, B, and C. So where does the equilibrium constant come from? All right, so it comes from the free energy. So the free energy has a number of different relationships. So first off, let's remember that delta G0 equals delta H0 minus T delta S0. Delta H is the enthalpy, which is the bonding energy. So this is the energy that is either required to break a bond or that's released when we form a bond. T is the temperature in Kelvin. Delta S0 is the entropy. And remember that the entropy reflects the disorder in the system. Oftentimes, when we talk about organic reactions, we'll focus mostly on the enthalpy. We can also describe the change in free energy for a reaction by saying that delta G0 equals the G0, the free energies of the products, minus the free energies of the reactants. Okay? And we can tie this to the equilibrium constant by the expression delta G0 equals minus 2.303. This is just a conversion of natural log to log base 10 times RT log equilibrium constant. Okay, R is the gas constant and T is the temperature in Kelvin. All right, so from this relationship between delta G and the equilibrium constant over here, we can predict a few things. Let's rearrange this equation to solve for the equilibrium constant. If we do this, K equilibrium is going to equal 10 to the minus delta G0 over 2.303 RT. And I put this in parentheses. So now let's compare to what we wrote for the equilibrium constant up above. So if the equilibrium constant is greater than 1, we know that this favors the products. But what does this mean about the change in free energy? So if the free energy, if the equilibrium constant is plus, and we have this minus up here, then delta G0 must be minus here because a minus minus gives a positive exponent. And so we get a positive or an equilibrium constant greater than 1 if delta G0 is less than 0. Alternatively, if we have that K equilibrium constant is less than 1, like we wrote above, this is going to favor the reactants. And in order to have it less than 1, we need a negative exponent on 10. And so if delta G is positive, that will give an overall negative exponent. So this would be if delta G0 is greater than 0. Right? So negative delta G's will favor products. Positive delta G's will favor reactants. We won't be doing any of these types of calculations in this class, but it is important to remind ourselves of these relationships. Well, thermodynamics describes equilibrium. Kinetics describes the rate or the speed at which reactions take place. One of the important things that we need to do relative to kinetics is to write out rate equations or rate laws. So if we have a reaction that starts with one reactant A, which splits into two other pieces, we could write the rate equals K. Remember, K is the rate constant. And this is a constant for this reaction at a given temperature, pressure, concentration, that kind of thing, times the concentration of the reactant A. So a fast reaction will have a large K, slow reaction will have a small k, but notice that the rate of the reaction is directly proportional to the concentration. If the rate is dependent on the concentration of a single reactant, then we call it a first order reaction, or we could likewise call it unimolecular. If we have a reaction that has two reactants, A plus B, going to C, then our rate will be K, the rate constant, times the concentration of both of the reactants. So if we increase the concentration, or if we double the concentration of A, then the rate will double. If we double the concentration of B, the rate will likewise double. What happens if we went 2 times the concentration of A and 2 times the concentration of B? Well, then the rate would go 4 times faster. This is referred to as a second order reaction, or it can be called bimolecular. All right, so if we look at a reaction shown at the bottom, this to come up with a rate law would really take some experiments to determine the relationships. So remember from Gen Chem what we would have to do in this case is we would have to hold one reactant's concentration fixed while we vary the concentration of the other reactant, and we look at the relationship to the rate. Then we would do another series of experiments where we would hold the other reactant's concentration fixed and we'd vary the concentration of the other reactant. And that's the way how we would actually determine the rate law. And so for this reaction, we'll learn about this later and we could predict the rate law. The rate law here is going to be equal to K times only the concentration of the alkyl halide, even though water is listed as a reactant in the reaction. So what this means is that there are more than one step. One step is going to be the rate determining step, and the rate law only reflects the rate determining step. All right, so as we learn new reactions, we'll continue to discuss the issues of thermodynamics and kinetics for each of the reactions that we learn.